Where's my pen? It's here. I provide two proofs for Trolexy theorem. Both of them are good. I went for the second one because the one which is in book, and I couldn't see what's going on. And trying to see what's going on, I came up with the second proof, which probably even sheds more light on the proof. So let's go with the proof which is provided in the book. Our goal is to show that the matrix Pij minus Pik Pkj divided by Pkk is positive. But recall that by assumption Pkk is strictly positive. So this is equivalent to show that Pij, Pkk, we multiply by Pkk. Is bigger than or equal to 0. So it's a matrix whose ij element Qij is equal to this one. And this is equivalent to, our goal is to show that sum over I and j, alpha I, alpha j, and say, let's put bar on this, Qij bigger than or equal to 0 for any alpha in Cn. We need to show this. This is our goal. How do we do that? Our assumption is that P is positive. So assumption P is positive, which is equivalent to say that Px and x is positive. Or if you wish, we can write it this way too. Sum ij from 1 up to n, Pij, I write later. Xi bar xj Pij is positive for every x in C. And we know this. This is our assumption. So this is our assumption. And the idea in the proof is to choose a good choice, a good candidate for x, such that when we do the simplification, we obtain this one. Even at the very beginning, the components of x are given. And when we plug the component inside, we see that it works. xi are defined this way. Xi is equal to root of Pkk alpha I if I is not equal to k, and xk, it's minus 1 over root Pkk sum j from 1 up to n, j not equal to k, Pkj alpha j. And the rest is just calculation. It means that we plug xi here, x and xj there, and we simplify. And then after a few lines, we arrive at this. That's the whole story. I try to explain a little bit, but and that's precisely the point when I said, why this choice, where it does come from. And I try to understand this better, and that is why I came up with a second proof, which I show you later. Well, a little bit on more the proof. Px and x, as we saw, is the sum ij from 1 to n, xi bar xj pij, and then we divide it into 4 groups. One group is just one element pkk. Another one, the one which are above it or below it. Yet another group on the same row, and the rest. Do we have any other color? Yeah. And the one which are here. That's the way we divide this sum into 4 sums. So it's sum ij from 1 up to n, I not equal to k, j not equal to k, xi bar xj pij. This is our big sum. Then class. Another one is sum I from 1 to n, I not equal to k. Same thing. So here I changes from 1 to n, so this is our other one. Plus the same thing with j. Did I write it correctly? Oh, there is one thing which I didn't write correctly, is this one. K. We are on the column K. And then, so now we are on the row K, so xk bar xj pkj. Here is this color. And finally, just 1 point plus xk bar xk pkk. It's just the green one, just 1 point. So that's the way we divide our sum into 4 sums. Now we know what is xi and xj in each case. And that is the reason we do this, because the formula for xi is different when I is equal to k. So here we know what to put for xk, the same here, the same here and there. And for all other values, xj, xi bar, or xj here, I is not equal to k, j is not equal to k. And we use the other formula, this one. So everything is known. The rest is just plugging. And when you plug, so I don't do the rest, some calculation. And at the end, what you obtain is precisely sum I and j from 1 up to n, alpha I bar, alpha j, qij bigger than or equal to 0. Just simple calculation, and we obtain the result Q0, end of the story. So it's quite a straightforward proof, except that you don't know where this comes from. Where does this come from? And to do this, I give you another proof. Before proof, remark. If you have a matrix S, which is invertible, then matrix A is positive if and only if S star AS is positive. Indeed, invertibility is needed here to have both-sided. If S is not invertible, just a matrix S, then we have one direction. A positive implies that S star AS is positive. For any S, this is true, but the matrix I use here is invertible, so we have both. And it's enough to give the proof for one direction because if it is true for one direction, for example, for this one, then we simply multiply by S star minus 1 and S minus 1 from left and right, and we obtain the same thing. So, and the proof is very straightforward because S star AS acting on X inner product with X is A SX and SX. So it's like AY acting on Y when Y is SX is in our space, whatever it is, H. And so if A is positive, then this is positive, and which implies that S star AS is positive. It's a very simple observation. And this observation is used in the second proof that I present here. We have the matrix P. Here is PKK, which is not 0. Some elements here. And now try to multiply by a matrix such that, I mean, call this matrix S1, such that if you do PS1, then the element here is 0. Kind of linear operation. Of course, the elements on the so which one I choose? C1, PKK. The I one, sorry. Not necessarily on this one. So here is PKK. I want to do some operation such that, yeah, what I said is true. I want to make these elements here one by one to be equal to 0. But I do it one at a time, not everything in one shot. So we have elements here. I want to do an operation such that this element is 0. What is this one that you suggest? If I use the same notation that I use in a course I gave about 2 years ago, it's called Introduction à l'analyse. It's very elementary analysis. The thing we do is that we replace the column 1 by column 1 minus a coefficient column k. This is not an identity in the language of mathematics, it's an identity in the language of computer programming. So the new C1 is the old C1 minus eta times CK. And eta is adjusted such that when we do the operation, the result here is equal to 0. And it's easy to see that it has to be C1 minus PK1 divided by PKK CK. That's the operation we need to do. And the matrix we need, S1 is this matrix. C1, 0, minus PK1. When we multiply by this, no, it has to be here, sorry. Minus PK1, PKK, here is everything 0. And on the diagonal equal to 1. Everywhere else equal to 0. So when you look at column 2, column 3, up to column n, it's just E2, E3, En. So when you multiply S1 by P, column 2 doesn't change, column 3 doesn't change, and column n doesn't change. But column 1 changes. Column 1 is 1, which is used here, times column 1 minus this eta times column k. And eta is adjusted such that this, when we do the multiplication, the result here is equal to 0. So it's a matrix which is basically the identity matrix, except at one point. We replace it by minus pk1 divided by pkk. And the question is that now if I do S1 star PS1, what do I obtain? You should immediately see that. Note that when I multiply it from the right, I do operation on the columns of P. So naturally, when I multiply from the left, I do a similar operation, but on the rows of P. So when I do this, the result will be a matrix, which is PKK, 0 here, 0 here. And of course, the other elements here, they change. I mean, the elements here and here and here and here are changing because I do column 1 equal to column 1 minus a constant times column k, and the same for row 1. Row 1 would be the same as row 1 minus another constant row k. Everything else is remaining the same. So it's just an operation. S1 star times P times S1 is an operation that we do on P. And we do this operation just to obtain a 0 here and a 0 there. If you ask, what are these new elements here? You have seen them before. You have seen them before. These are precisely this element, but just for row 1 and column 1. Do the operation, you'll see them. It's Pij minus Pik Pki divided by Pkk. For I equal to 1 gives you the element here. And for j equal to 1 gives you the element there. True. And repeat this operation now with goal of, on this matrix, find S2 such that when you choose 2 star, S2, the result is the matrix we had before, but now 2 zeros. And because of the 0, which we already created, these do not change. These that element that we had before, they remain the same. But we have a new set of elements, the one here, the one there, and the one there. And they are again given by the same formula that we saw before. And repeat this for all n-1 elements which are here to make zeros above, below, on the right, and on the left side of PKK. And what you obtain at the end, if you repeat this operation, and you call S equal to S1, S2, Sn-1, what you obtain is S star PS, almost the same matrix that we saw above. It's almost this matrix, the one that we want. Almost this one. Why I say almost? Because what we obtain at the end is a matrix that here is not 0, PKK remains. In the previous matrix, here is also equal to 0. All elements in this row and in this column are 0 because of the operation we did. So 0 here. And the rest is precisely what we are looking for. The elements here in all 4 corners are Pij minus Pik, Pkj divided by Pkk. So it's almost the matrix that we have before. And we know P positive implies that S star PS is positive. So this matrix is positive. And if you remove a row and a column of the same order, here is row K and column K, what is remaining is still a positive matrix. So if you completely remove this and remove this, so PKK, you also remove it, you obtain a matrix which is n-1 by n-1, and that matrix is positive, which is equivalent to what we wanted to do before, because it is true that the previous matrix is n by n. This is n by n, but everything in the case row and case column is equal to 0. So in practice, it's just n by n-1 by n-1. True. So that's a proof that, I found, more instructive if you explain properly by this proof, that we do elementary operation to make some element equal to 0, and what remains is what we saw above. That's, I don't know if, Sheldon, do you agree with that? You're an expert in linear algebra.
Yes, that's a very nice proof of the Trolexy theorem. Yeah. I like it a lot.
Thank you. But I repeat, the only difference is that what remains at the end is PKK, but here it really doesn't matter.
Right.
Yeah. So we obtained something which is still a positive matrix. And this leads us to a theorem which is called Trolexy factorization theorem. But how did we obtain this matrix? So this is important to recall. So recall. We started with matrix P, but to obtain the matrix whose case column and case row both are equal to 0, we did this operation. We did P minus 1 over PKK. It's better to write CK. Still I use K, my apology, Sheldon, this is my notes. CK for the K columns of P and CK star. This is what we did above to obtain something which is positive. So that's the matrix whose case row and case column are equal to 0. We did this. And P, we look at it. I try to change my notation later on. We look at P as columns like this. So if we do P minus 1 over PKK, CK, CK star, we obtain a matrix, which is still positive, but practically the new matrix is n minus 1 by n minus 1. And that's the beginning of Trolexy's factorization theorem. So here is the theorem. Trolexy's factorization. Let P be an n times n positive matrix. Positive here, I mean, I mentioned in one of the lectures before, for us it means bigger than or equal to 0, but it's not, I mean, something universal. For some authors, positive means strictly bigger than 0. Here, means bigger than or equal to 0. Then there exists a lower triangular matrix L for lower, such that P is equal to L star. Of course, the reverse is trivial, because if we know that, what's a comment? If we know that P is equal to LL star, then PX scalar X, C is LL star X, we can take L to the other side. It's just normal star X. It's positive. So P is positive. If we have this shape, this form, then P is positive. The reverse order is important. And we do this by induction. By induction. If P is 1 by 1 matrix, just one element here, P positive is equivalent to that component being positive. And so we can take root square. So L is root square of P11. And we see that LL star, is it LL star? Or yeah, L star is just P. So kind of trivial, but it's still important. And now assume that the result is true for n minus 1. And look at the element P11. There are two cases. Case 1, P11 equal to 0. Then by the lemma we had at the very beginning, the first column and the first row, both of them are, identically equal to 0. P1j is equal to P I1 is equal to 0 for all I and j. In other words, our matrix P has this form. Everything here is equal to 0. And the remaining is a matrix Q, which is n minus 1 times n minus 1. P positive implies that Q is positive. The order of Q is n minus 1. We can use our induction hypothesis. For n minus 1, the decomposition works. So there is a matrix L1, n minus 1 times n minus 1 lower triangular, such that Q is equal to L1, L1 star. And now we define L precisely as we have for P here. We just, instead of Q, we plug L1. So define L by this formula. Instead of writing the formula, I do it a diagram. You understand what I mean? So here, 0, first row, first column also equal to 0. So these are all 0. And then I put L1 here. And note that L1 is lower triangular. So everything here is 0 and L1 is there. This 0 is also part of L1, this one. But this way you immediately see that L is lower triangular. Triangular. In standard books, sometimes they write it this way too. 0, 0, 0, L1, which is true, very good, but you need to be careful that these zeros are not the same. The first 0 here, let me erase the colors here to explain. The first 0 here is just a scalar. The second 0 is this part of the row, and the third one is this vector. So even though we write 0, 0, 0, you need to be careful what they mean. But still it works, and there is no danger of writing this composed matrix. And sometimes they even add some dot lines like this. And then when you do L times L star and L times L star, in particular with this form, it's easy to see what is L times L star, because even though, as I said, zeros are not the same, but there is no danger to write it this way. It will be L1 star. All dimensions work perfectly, and there is no problem with that. Is our true. Again, to respect the color we had before, if you write this as green, then it becomes like that. And the same for the other one, this becomes like this. But I mean, after the multiplication, everything works well, and there is no problem with that. So in this case, it works well. If the first element is equal to 0, if not, case 2, if P11 is bigger than 0, then we use the previous theorem of Trolexy, the main observation. And by previous theorem, P minus 1 over P11, and then we had column 1 star is still bigger than or equal to 0. And we end up with the same story again, because now if I already use Q, P, Q, let me call this matrix R. Again, R has the form, 0 here, 0 there. When all elements here are 0. And there is another matrix S here, but S is n minus 1 by n, n minus 1. So this is n minus 1 times n minus 1. And you do the same thing. You do the same that we had before with S, and we proceed as before. So by induction, there is L1. It's not the same L1 as before, but it's okay. We can write it that way. N minus 1, n minus 1, lower triangular, such that S is equal to L1, L1 star. And now we define L by this formula. Define L. From this, you see what is your first column. Note that P1 is positive. So instead of P1, we can write root square of P11 squared. So we give one of them to C1, one of them to C1 squared. So our first column here would be 1 over root square of P11 C1. This is the first column here. And then here is completely 0. And I put L1 beneath this, but again, L1 is lower triangular. I put L1 here. And this 0 also belongs to L1. But I write it that way. And you see immediately that L is n by n, lower triangular. And just do the multiplication. L star is equal to P. In a sense, this finishes the proof, But there is more in the proof than stated in the theorem. And the more is what we see here. We start with P. We do P minus 1 over P11, C1, C1 star. Then we obtain a matrix which is positive, but a column and a row are equal to 0. So we can do the same. And for the rest, column 2, column 3 up to the end. And this gives us an algorithm to decompose a positive definite matrix. The algorithm is like this. How to detect if a matrix is positive definite or not. So A is given generally. A equal to Aij n by n is given. The question is indeed two questions. Question 1 is that is A bigger than or equal to 0? And question 2, if yes, give the decomposition. And here the way the algorithm works. You start with any element in the diagonal. I mean, either A11 or A22 or ANN, any one you wish. If A is bigger than or equal to 0, all of these have to be positive. So if by any chance you have a matrix such that on diagonal, you have something which is a complex number, not real, or real but negative, then for sure that matrix is not positive. So the answer to the question 1 is no. So if any of this is smaller than 0, or belong to C not R, then for sure A is not positive. So that's the first thing to check. Second, assume that all of them are positive. If one of them, say A11, is equal to 0, anything on the diagonal is equal to 0. The first result tells us that everything on the column of that element and on the row of that element must be 0. So this, we need a first row A1j to be 0 for Rj, and first column AI1 to be 0 for all I. If any of these is violated, then P is not positive. If not, P is not positive again. If yes, what do we have? We go to we start all over. With n minus 1 times n minus 1 matrix. So remember, we started with an n by n matrix. It's n by n. If we ended up here, everything in the first column and first row equal to 0, or doesn't matter, the third column and third row, everything 0, we can forget about this and start all over, but with a matrix whose order is less, n minus 1, n minus 1. But this is for the case if A11 is equal to 0. If not, if A11 is strictly bigger than 0, consider matrix P minus A11, column 1 star, no, column 1, column 1 star. We consider this. We know P minus 1 over A minus 1 C1 star is positive. And also the first column and the first row are identically equal to 0. So again, we are in this situation. Start all over with an n by n minus 1 times n minus 1 matrix. It's the matrix. So in briefly speaking, you have a matrix like this. This is your P. And in the first step, even if instead of P11, I write P11, the root of P11 squared and done one root to this one and one root to this one. I start with P, and then I have P minus, let's call it L1 star. And this gives me a matrix such that this is 0 and this is 0. This is my matrix P minus L1 star. And then I do this one more time. And I do it one more time if still the algorithm doesn't tell me that the matrix is not positive. Then I continue and I obtain the matrix. Here is P minus L1 star minus L2 star, such that here and here everything is 0. And the remaining one is n minus 2 times n minus 2. And I continue this up to the end. At the end, what do I obtain? If it is successful up to the end, if the algorithm does not stop, at the end, I obtain P minus L1 star minus L2 star Ln star equal to 0. It's a matrix which is identically equal to 0. Of course, it is possible that somewhere in the middle, the algorithm breaks and says that the matrix you have is not a positive matrix. So we go back and the one we started with is not positive too. That's a very good and effective and fast algorithm to do two things. You see, at the end, we have obtained two things. Back to the questions. I have two questions. Is it positive? If we go up to the n successfully, the answer is yes, if we have equal to 0 at the end. And if yes, we have something more. We have P equal to L1, L1 star. And what is L1? L1 is just a column. Instead of C, I wrote L. Indeed, I should have kept C. So we can write P as a sum I from 1. Even we might stop at in the middle. It's not necessarily up to the end. Maybe somewhere in the middle we arrive at 0. And allow me to write a star, then A is a column, AI star. So we have a decomposition like this too. And this is another form of the Trolexy's algorithm. And even still, we can say even more. I mean, the first column that we have, sometimes this is useful. The first column we have is the first column of P, but the second column is the first column of this matrix. So its first component is equal to 0. And for the third one, the first two component is equal to 0. So we can write it this way. And indeed, this information were provided before, but in kind of disguised form, because when we say that L is lower triangular and P is equal to L star, you remember at the beginning of this, we said that at least there are 3 or 4 interpretations for the product of two matrices. One of them is to consider the column of the first one and the rows of the second one. So here we can consider P and the columns of L. There is no danger now if I write L1, L2, Ln. You understand what I mean? And the rows of L star, and you know what are the rows of L star are, because it's L1 star, L2 star, Ln star. And we saw that this multiplication is precisely L1, L1 star, the first column, the first row, second column, second row, and Ln star. And note that each of these by itself is an n by n matrix, but a very particular one. And as we proceed in L2, because it's lower triangular, in L2, we have 1, 0 here. In L3, we have 2, 0, and in Ln, we have n minus 1, 0. This is what I mentioned here, that there are more information inside this decomposition. But it was indeed hidden in the theorem of Trolexy too. But with this algorithm, you really see what's going on. And it's a very fast algorithm to detect if something is positive or not. I started with P11, but for a stability reason, this is something that people in numerical analysis, they consider. Instead of working with P11, they look at the diagonal and choose the biggest element. And because we divide to that biggest element, it's more stable. So if, for example, an element here is the biggest one, they try to make this column equal to 0 and that corresponding row equal to 0, and then continue the same. At each time, they don't go in order. They consider the greatest element on the diagonal and they divide by that element and go up to the end. Very good. So now you have a very effective argument to detect if something is positive or not. After the break, I'll give another interpretation for Cholesky's algorithm, and then we'll go to sure products, or I mean, sometimes they call Hadamard products too.